All right, let's start this deep dive. We are getting very specific today with a single piece of infrastructure hardware.
A really interesting one, too.
Yeah, the Thor broadcast, F-RF-TxRx-MN2. And the mission for you listening is to really understand how this device acts as a fundamental physical security break in a network.
Right.
We're moving way beyond the usual fiber benefits like speed or distance.
And the whole premise here is, well, it's pretty high stakes. Our sources establish that in military and high-security applications, traditional coaxial cabling is seen as a serious security vulnerability.
And we're not just talking about potential hacking, are we?
No, not at all.
All right.
This is a physical flaw that this specific piece of hardware is built to fix.
Okay, but that brings up a question for me right away.
Mm-hmm.
If the risk is just a two-way signal path, why can't a high-security facility just use, I don't know, advanced filters or some kind of software block? Why do you need this whole dedicated box?
That's the core of it, really. It's the difference between isolation and filtration.
Okay.
Coax is inherently bidirectional. Physically, it's capable of carrying a signal both ways. A filter is it's an add-on. It can fail, it can be bypassed.
It can be compromised.
Exactly. This Thor unit, it implements what's called an RF fiber break. It forces the signal onto a single directional fiber link. There is no return path by design.
So it's like a physical one-way street, a turnstile.
It's the perfect analogy. The structure itself prevents movement in the opposite direction. That's the absolute signal isolation they need.
So the physical security is solved, but a one-way path is useless if the signal itself degrades. How do they make sure the secure link doesn't compromise the signal quality?
Well, they engineered this thing for pristine delivery. Beyond security, they focused on, and I'm quoting here, excellent linearity and flatness.
And I saw they use ultra-low noise technology.
That's right. And what's fascinating is how they do this while still being super adaptable.
Let's get into those specifics then. It operates in the CATV band, right?
Yes.
45 to 870 millihertz, up to 1,000.
Correct. And it uses an optical wavelength of 1,310 nanometers.
So for you listening, why is that specific wavelength important for a secure device?
It's the industry standard for minimizing dispersion over, shorter haul single mode fiber.
And these would be shorter runs.
Yeah.
Inside a facility.
Exactly. You need maximum fidelity over that short distance. Then once the light hits the receiver, it converts right back to an electrical RF signal that's compatible with basically every video standard on the planet.
Like analog NTSC, PAL.
Or digital QAM, ATSC, DVB-T. You can plug it straight into existing secure infrastructure. It's ready to go.
The quality metrics listed seem to back that up. We're seeing link CCTB performance of greater than or equal to 65 dBc.
Yeah.
And a link CN of over 51 dB. Those numbers sound impressive, but what do they fundamentally guarantee?
They guarantee purity under pressure. The first one, CCTB, measures nonlinear distortion, basically, how much unwanted noise the gear generates itself.
Okay.
A score of 55 or higher is excellent. It tells you they've engineered out virtually all that internal noise.
And the carrier-to-noise ratio.
That CN score of 51 dB ensures the protected signal stays crystal clear, even with electrical background noise. High security demands high fidelity.
That makes perfect sense. Security and performance are two sides of the same coin. What about the build itself? In these environments, physical tampering is always a risk.
Absolutely. And the structural details confirm that security-first mindset. The housing is stainless metal.
Tough to get into.
Very tough. It resists tampering, and it's also effective for RFI shielding, so no signals are leaking out or getting in. On top of that, it has a low-power launch design. The transmitter uses less than 8 watts.
Why is that so important?
It minimizes heat generation, which reduces the device's thermal signature. And that is a huge factor in any secure monitoring setup.
And I noticed the receiver has a dual coaxial output. That feels like a practical touch for deployment.
It is. It means a single secured optical feed can convert back to RF and immediately feed 2 separate devices without needing an unsecured splitter.
So if we pull this all together, what's the key takeaway?
I think the key takeaway is that when you see a move from copper or coax to fiber in these high security environments, it isn't just about bandwidth or distance.
It's not just for speed.
No, it's fundamentally about achieving absolute physical security and signal isolation. Every single design choice, from the one-way light path to the steel housing and the low power draw, it all serves that one single goal: physical control over data flow.
So what does this all mean for you? If a simple coaxial cable, a piece of tech we all know, poses a serious security vulnerability just because of its inherent signal directionality,
Hmm.
it really encourages you to consider the unseen risks in other common connectors you use every day. Are any of your daily connectors unintentionally exposing sensitive data just because of how they're built?
It's a great question.
Yeah. Is it a two-way street when it really should be a one-way? That's a compelling thought experiment for your next hardware purchase.